In the previous couple of videos, I introduced Noether's theorem. For every continuous symmetry in nature, there is a conserved quantity. I then used this to examine global symmetry with respect to position and time displacement, and explained that these resulted in conservation of momentum and conservation of energy and mass. Next, we saw how local transformations of space and time resulted in gravity, and this was caused by the presence of the conserved quantities. The reason I started with gravity is that the number of new things you have to learn was smallest. Noether's theorem and the bending of space-time coordinates might have been unfamiliar, but space, time, mass, energy and motion are all familiar concepts. We're now going to follow the same pattern again. We'll examine a global symmetry, identify the conserved quantity, perform a local symmetry transformation instead of a global one, and see what the resulting force of nature looks like. Each time I repeat this exercise, it's going to involve something new. The thing that's new this time is that, unless you're familiar with the physics, the symmetry is almost certainly going to be unfamiliar to you. I'm going to start by reminding you what a probability distribution looks like. Suppose I throw an object on a table. For the sake of argument, let's assume that the table is 30 centimeters long. So the object can land at any position from 0 to 30 centimeters. I'll try not to throw it off the edge of the table, meaning that I'll try and aim somewhere near the middle of the table. Positions near the 15 centimetre mark are probably more likely than positions at the ends. So the probability distribution of landing in a particular position is going to look something like this. There's going to be a high probability of landing somewhere near the middle of the table and a relatively low probability of landing at the end somewhere. Now, the thing I want you to notice about this graph is that along here, this is a position axis. But along this axis, we have something that has nothing to do with position. It's an abstract mathematical function. It's a probability. We have a very similar thing in quantum mechanics called a wave function. The horizontal axis here is position in just the same way as this was position for the object that I threw on the table. And just as here we measured probability along this axis, here we've also got a measure of probability along the vertical axis. Incidentally, you might have heard that things sometimes behave as waves and sometimes behave as particles. That's just because the wave function can have very different shapes. If it's long, drawn out and regular, like this type of sine wave, then the particle is behaving like a wave. If it's very sharply peaked, then it behaves more like a particle at a fixed position. Most of the time, it's somewhere in between. Now, as I said, this vertical axis here is not a distance in space, it's a measure of probability. Except in quantum mechanics, there isn't just one of these abstract axes. There are two of them at right angles. Just to give them names, I'm going to call one of them A, one of them B, and I'll call position the x-axis. So this is still distance, just as it was here and here. And these two axes combined are something to do with probability. The wave function looks more like a spring or a corkscrew that wraps around the position axis. Just remember that only the horizontal direction is in real space though. The probability is found using the distance from the x-axis. Now we can come to our global symmetry. Imagine rotating the wave function around the x-axis. Nothing has really changed. The initial direction of our A and B axis was arbitrary. We can rotate them through the same angle as the wave function. Everything will end up looking exactly like it did before. all the probabilities, all the distances from the x-axis, will remain exactly the same. So this is our new global symmetry. And thanks to Noether's theorem, it tells us that there's something that is conserved. Mathematically, the thing that's conserved looks very much like angular momentum. Now in mechanics, angular momentum is a measure of how much stuff is going around an axis and how fast it is moving. So more stuff means more angular momentum, and going faster also means more angular momentum. Now, in quantum mechanics, an important fact about angular momentum is that it's always quantized. You can't just have any old value of angular momentum. It always comes in discrete packets. And because a thing can spin about an axis in two ways, it can go either this way or it can go that way, clockwise or counterclockwise, the spin can be described as either positive or negative. The conserved quantity here is not mechanical angular momentum because it's not rotation in space, it's rotation about the AB plane. But just like angular momentum, it comes in discrete packets and can be positive or negative. It's electric charge. The symmetry we've discovered is a global symmetry. Our conservation law is also global. All it means is that the total electric charge in the universe is constant. But we know that there's more to electric charge than this. Suppose we've got an electric charge over here. If it suddenly vanished and instantly reappeared over here, then the total charge would still be conserved. But that's not what we observe. To get from here to here, the electric charge has to move along a path between the two endpoints. Electric charge is conserved on the left hand of the drawing board and on the right. It can't just hop from any one point in one half of the board to some other point in the other half. This means we can apply Noether's theorem to just each half of the board. A transformation on the left half preserves charge on the left. We can make the area where we perform the transformation smaller and smaller. Eventually, we arrive at a purely local transformation that includes just the individual charge itself. We've turned a global transformation into a local transformation, just as we did when we were looking at gravity. If you imagine the wave function as a spring, then we're now rotating the spring by different amounts at different locations. And just as it would do with a spring, this creates tensions. If you twist the spring in only one place, or in different amounts at different places, it creates a force in the spring. If you then release it, then it tries to pop back into its original configuration. Something very similar happens when you twist the wave function in only one location. It creates a force. Now there are quite a few constraints on this force. For one thing, just like electric charge itself, it can't just jump around all over the place. It has to respect causality. In physics, this means it has to obey the rules of relativity. Secondly, it mustn't break the local symmetry. These two constraints effectively dictate the form that the force will take. When we calculate this form, we get the laws of electromagnetism. We can actually derive Maxwell's equations from this symmetry. And these are Maxwell's equations. It doesn't really matter if you don't understand what all the symbols mean. They tell you how electric and magnetic fields change in response to one another and in response to currents and charges. They're the crowning glory of 19th century physics. They united electricity and magnetism. They explained the nature of light and predicted radio waves. They give us a firm understanding of how to build electric motors, generators and communications equipment. Much of the industrial world has been built on their application. They were the inspiration for relativity. Combined with quantum mechanics, they explain the periodic table of the elements, chemical bonds, and so the whole of chemistry and biology. This table, this pen, the ink in the pen, their properties are all down to electromagnetism. Everything you have ever touched, smelled, tasted was down to electromagnetism. Everything you ever thought or loved or hated or believed depended on the action of electromagnetism. What you're seeing on the screen just now, the screen itself, the sound of my voice, they're all electromagnetism in action. Almost everything we know about the world or the wider universe beyond is due to us seeing the world via electromagnetism. And that all happens because there is an invisible rotational symmetry hidden in every point in space. And that is simply astonishing.